When we use the buoyancy force, we should think about the normal forces things we've learned in AP Physics all along. Newton's second law, F net equals ma. Let's do a number of problems wrestling with the buoyancy force to help you get a better sense of what this force is and how to calculate it. Let's imagine there's a block at the bottom of a tank of water. Let's imagine the volume is 0.3 meters cubed and the mass of the block is 500 kilograms. So it's a big, heavy block. Let's calculate the force of normal. How would we do that? Well, we always calculate the force of normal by thinking about the free body diagram. So let's draw the free body diagram. For the block submerged underwater, there are three forces. Force of buoyancy going upwards, force of normal going upwards, and the force of gravity going downwards. If we think of a block sitting in a normal area, there would be two free body diagrams, a force of gravity going downwards, normal force going up. That's sort of an ordinary situation. So here, when it's underwater, there's one additional force that's going upwards, the buoyancy force. Now we should write down Newton's second law. The net force equals ma. So the net force is going to be these three forces added together. It doesn't matter which direction we choose to be positive. Let's say the force of gravity is positive, downwards, and that means the net force and the buoyancy force are negative. And we should put acceleration as 0. This block here is not moving or accelerating. It's not accelerating up, it's not accelerating downwards. So the total acceleration is 0. We say the forces are in balance when the acceleration is 0. That is, the net force is equal to 0. Boom. If we rearrange this, we can get the force of normal is going to be the force of gravity minus the buoyancy force. Great. We know that the gravity force is mg. And what's the buoyancy force? That's going to be the one we looked at in the last video, rho vg. So let's put those in. So we have numbers for all of this, so let's put the numbers in. So the force of gravity is going to be 500 times 10. The buoyancy force is 1,000 times 0.3 times 10. Remember, the density of water is 1,000 kilograms per meters cubed. So what do we get? We get 5,000 minus 3,000. That is, the force of gravity is 5,000 downwards. The buoyancy force is 3,000 upwards. That means the net force should be 2,000 newtons. Okay, very good. This block at the bottom of the tank of water will experience a net force, and it's going to be 2,000 newtons upwards. Great. I just want to point out one idea that's kind of hidden inside this equation. This here, the force of gravity, that's the weight of the block. This here, rho v, that has to do with the buoyancy force. But what's this? Remember that the density formula connects density, mass, and volume. Rho is velocity over mass. If we rearrange that, we get mass equals rho times v. That there. Now, the rho that's here is the density of water, and the v is the volume of the block. But we've said before, this is a displacement volume. So this volume is the volume of the water displaced. That is to say, this term is the mass of the water displaced. So what's going on here is the force of gravity of the block is larger than the force of gravity that's on the volume displaced, which means the block is going to sink downwards. Again, when the gravity force is larger than a buoyancy force, it will sink all the way down, and it's going to accelerate downwards until it gets to the bottom, and then there's a force of normal going upwards to stop the acceleration. The best way to improve your grade is with a practice test. On my website is a fluids practice test. Click the link below to get a free practice test. We'll even mark it for you. Let's try calculating what the acceleration of this block would be in the water. So let's imagine that block is floating in water and it's sinking downwards as it's suspended in the water. So we need to change the free body diagram because now there's no normal force. So instead of the forces being balanced, now there's an excess force downwards because the force of gravity is greater and it's going to sink downwards. So let's try calculating that. We've already seen that the force of gravity is 5,000 newtons. The force of buoyancy is 3,000 newtons. So we're going to get the force of gravity minus the buoyancy force divided by the mass is going to be the acceleration. If we put all the numbers in, we're going to be able to calculate for the acceleration. We get 5,000 minus 3,000 divided by the mass. We get 2,000 divided by 500. That's going to be 4 meters per second squared. So this block will accelerate downwards at a rate of 4.0 meters per second squared. And that kind of makes sense. The gravity is 9.810 meters per second squared downwards. So the buoyancy force is slowing the block down, meaning that it doesn't go down as fast, but it still goes downwards. Okay, let's do another example of just calculating buoyancy forces. Let's imagine there's a block that's in a tank of unknown liquid floating in that fluid. And there's a crane pulling it upwards with a force of tension upwards. And the block is accelerating upwards at a certain rate. So we don't know the density of this fluid. I'm going to ask us to calculate the density of this fluid in terms of the variables in this question. We have the mass of the block, the volume of the block, the force of tension, and the acceleration. So what will the density be in terms of these variables plus any other constants that we know? So let's again begin by a free body diagram. This block has 3 forces, 2 forces going upwards, the force of normal and the force of buoyancy. Remember, the force of buoyancy is always pointed upwards. There's the force of gravity going downwards. And now the forces are non-balanced as the next force, and this time it's pointing upwards. The crane is lifting the block out of the liquid. So we can, as always, write down Newton's second law. So here for the net force, I'm going to put the upwards forces as positive and gravity as negative. So the question is asking us to solve for rho. So I'm going to put all my variables in for the buoyancy force and the gravity force. And rho is going to be a term inside the buoyancy force. So I'm going to have to arrange a few things around and solve for that. So force of tension equals rho Vg minus mg equals ma. So that m is the mass of the block and the volume is the volume of the block. Label it B for block. Okay, let's solve, leaving this side, this term on the left side, but everything else on the right side. We get rho Vg equals ma plus mg minus force of tension. This is the acceleration that's caused, this is the force of gravity term, and this is the tension term. We just solve for rho now, dividing by volume and g. We have an expression, a mathematical formula for rho, the density of the liquid. So we don't know what the liquid density is, but if we knew the numbers, we could find it there. And we can think about proportionality here. So if this is a heavier block, that would imply that the force of buoyancy is larger, which should mean the rho is larger. If this was a larger block, that would imply the force of buoyancy is smaller. So that would mean that rho is a smaller term, thinking from that. The word buoyancy is spelled kind of funny. B-U-O-Y, buoyancy. I don't know if you've ever thought about those things that float in the water in the ocean, but we call them buoys. But it's not B-O-Y, it's B-U-O-Y. Mind blown. Has this video helped you understand the force of buoyancy better? If there's anything you don't understand, comment below. I read all the comments of these videos, and if there's anything that you want to know more about, let me know. The best way to improve your grade is with a practice test. On my video, on my website, is a fluids practice test. Click the link below to get a free practice test. We'll even mark it for you.